Good evening everyone. So today we are going to start a new chapter which is about system of equations. So the idea is to solve the nth order differential equation. Let's assume that we cannot solve a fourth order or fifth order differential equation. So we can reduce it into n first order equations that would call as the system of equations, and then we'll see how can we solve the system of equation that gives us the solution of the nth order differential equation. For example, let's assume that we have y double dash minus x square y dash minus xy is equal to 0. It's a second order differential equation. Now let's try to have a system of two first order differential equation from this equation. So for doing this, what I do is that I assume y dash to be z. That gives me z dash is equal to y double dash. I substitute both the values there. So I will get, instead of y double dash, I have z dash minus x square z minus xy is equal to 0. It means my required system is y dash is equal to z and z dash minus x square z minus x y is equal to 0. Yes, and now if we can solve this system of equation, which means if I know the method to solve mainly the first order differential equations, then I can have the solution of the nth order differential equation. Consider the third order differential equation. Here I assume y dash is equal to z. That gives me y double dash is equal to z dash, and introduce one more variable w. So now my system would be, I have introduced three equations. So one is y dash is equal to z, next is z dash is equal to w, and the third one is w dash is equal to w minus x square z square. So linear system of equation of first order in general is given as dx by dt is a function of t x comma y. Similarly, dy by dt can be defined where x and y are a dependent variable and t is an independent variable. In this system, we'll focus on linear system only, which would look like dx by dt is a1x plus b1y plus f1, dy by dt is a2x plus b2y plus f2. Now if f1, f2 both are 0, we'll call it homogeneous system of equation. If they are non-zero, we will call non-homogeneous system of equation. So the idea remains same as in the case of second order homogeneous or non-homogeneous differential equation. And this is how the solution looks like, x is equal to x of t. So whenever we talk of the system, we always use this curly bracket on the left hand side. So now recall that if we have a second order homogeneous differential equation and it has two solutions y1 and y2, we used to say that c1 y1 plus c2 y2 is also a solution, which means the linear combination of y1 y2 is also a solution of the differential equation. Yes, and this solution c1 y1 plus c2 y2 is a general solution if y1 y2 are linearly independent. And to check y1 and y2 are linearly independent, we check that the Wronskian must be non-zero. So the same concept, same details will be used here. So we say that if homogeneous system has these two solutions, then the linear combination given in equation 3 is also a solution of the homogeneous system. And we say that the Wronskian of two solutions x of t and y of t can be defined as x1 y1 x2 y2, determinant of x1 y1 x2 y2. So these are the two solutions x1 y1 x2 y2. So to find the Wronskian, this is how we compute the Wronskian, and then we say that two solutions of homogeneous system, or for these two solutions, if Wronskian is non-zero, or it's same as saying these two solutions are linearly independent, then the solution given in equation 3 is said to be the general solution. Yes, I'm not discussing much about the theory because it is the same as we discussed for the second order homogeneous differential equations. So what we focus now is in the method for solving homogeneous linear system with constant coefficients. Yes. Now recall that what method you have used for solving the homogeneous second order differential equation with constant coefficient. The method we call is known as the method of undetermined coefficient, where you use to assume y of x of the form a e raised to the power mx. Similarly, if I have a homogeneous system of equation where a1, a2 and b1, b2 are constant, then to solve it, we'll use the method of undetermined coefficient, where we will take the solution of the form x is equal to a e raised to the power mt, y is equal to b e raised to the power mt. Now what we need to do, we need to find the value of m as well as capital A and capital B. In today's class, we will only cover the theory, so that in the next class we will do the exercises based on this theory. So to find the values of m and capital B, I substitute equation 2 in equation 1. If we substitute it, what will happen? Let's keep it like this and see. I will rub it later on. So my left hand side would become a m e raised to the power mt, then a1 a e raised to the power mt plus b1 b e raised to the power mt, and the second would be dy by dt. So bm e raised to the power mt, then a2 a e raised to the power mt plus b2 b e raised to the power mt. If I delete e raised to the power mt from both the sides, and I will take am on the left hand side, on the right hand side, similarly bm on the right hand side, I will get a1, sorry, let's rub this one. So I will get a1 minus m capital A plus b1b is equal to 0, and a2a plus b2b minus m and b2 minus mb is equal to 0. Yes, so what I get is the homogeneous system of equation. So first, so let me rub this one because it has been given below. So this is my homogeneous system of equation which is given in equation 3. Now the point is, what I am looking for is a non-trivial solution for homogeneous system of equation. Recall that homogeneous system of equation is always consistent, which means either there is a unique solution or there are infinitely many solutions. Unique solution means capital A and capital B is equal to 0, and for infinitely many solutions, there we can choose infinitely many values for capital A and capital B. Now the trivial solution is obvious. It means I am looking for the non-trivial solution. So how do I know that under what condition non-trivial solution exists, or under what condition the trivial solution exists? So if I see this system, then if I have to write it in the form of the matrix, then it is a1 minus m, a2 b1 and b2 minus m, capital A capital B, and this is 0 0. It means it is of the form kx is equal to 0. Now if this k is invertible, then my solution would be x is equal to k inverse 0, which is 0, which means the trivial solution, and it is invertible when determinant is non-zero. It means that for the non-trivial solution, I must consider the determinant to be 0. When determinant is non-zero, I am getting the trivial solution because inverse exists. So for non-trivial solution, I must consider determinant to be equal to 0. So consider the determinant of a1 minus m, b1, a2, b2 minus m to be equal to 0. That gives you a quadratic equation in m, which is known as auxiliary equation. So for non-trivial solution, I must consider the determinant of this matrix to be 0, that gives me a quadratic equation in M, which is known as the auxiliary equation. This equation has two roots. Corresponding to each root, I will get a solution. It means I will get two solutions. So M1, M2 are roots. So this is how the two solutions looks like. Now again, if you recall the undetermined coefficient, there were three cases. So the first one is when you get the real and distinct roots. In that case, the linear combination of these two solutions gives you the general solution. When equal roots were there, you used to consider a e raised to the power mx and a x e raised to the power mx. And similarly, there was the case for the complex roots. So in the next class, we will consider all three cases, and based on these cases, we will see how do we reach to the general solution. Okay, so that's all from today's class. Thank you.